Welcome to The Explainer. Today, we're popping the hood on artificial intelligence to uncover the sheer, mind-bending math and mechanics behind how AI translates languages so seamlessly. You know, if you've ever typed a sentence into Google Translate and just kind of marveled at how instantly and accurately it spits out the result, you are absolutely in the right place. We're going to completely demystify the black box of neural machine translation.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with the leap from code breaking to neural AI, then we'll see how seek-to-seek models work, move into training multi-layer RNNs, check out beam search and decoding, and finally wrap up with scoring and low resources.
All right, part 1, code breaking to neural AI.
To really grasp where we are today, you gotta look at language translation not just as some linguistic hurdle, but as this massive, evolving mathematical puzzle. It's literally taken decades to solve. The whole quest actually kicked off back around the Cold War era with pure code breaking. Then, for a super long time, we're talking from the 1920s all the way to 2010, the field leaned heavily on something called statistical machine translation. Basically, they built probabilistic models using massive, massive chunks of parallel data. They were relying on huge volumes of text that human translators had already converted. But the whole landscape completely shifted in late 2016. That's when Google Translate officially adopted neural machine translation. And this brilliantly illustrates that massive leap in architecture. On one side, you've got the old way, statistical machine translation. It was this clunky, piecemeal approach that basically scraped vast human-translated datasets just to guess probabilities word by agonizing word. On the flip side, modern neural machine translation. Instead of that multi-step mess, it relies on a single end-to-end neural network. It's this elegant, unified system that, honestly, completely rewrote the rules of the game. Moving on to Section 2, how seek-to-seek models work. Get ready, because we're about to meet the absolute hero of our story. This is the engine making all that modern translation magic happen. But before we get into the nuts and bolts, let me ask you, what exact architecture revolutionized Google Translate back in late 2016? Like, what specific deep learning blueprint did they drop in to make translation suddenly feel, well, human? Drumroll, please. The answer is sequence to sequence, which is short for sequence to sequence. I like to think of this as the ultimate journey of a sentence. At its core, a sequence-to-sequence model is just a deep learning architecture that takes a sequence of items, say a string of English words flowing in one after the other, and eventually spits out another sequence of items, like the exact equivalent series of words in French. So let's break down how that journey actually works in the pipeline. Step 1, we feed our source sentence into the first recurrent neural network, which we call the encoder. The encoder chews on each item and compiles everything it's learning. Step 2, it squeezes all that learned information into what's called a context vector. And then step 3, it hands that vector over to a second neural network, the decoder, which gets to work producing the final output sequence, piece by piece. Okay, so if we have these two totally separate networks, the encoder reading the input over here and the decoder writing the output over there, how does the data actually travel between them? What's the physical bridge between understanding a thought and actually speaking it? It travels through that context vector we just mentioned. Picture the context vector like a tightly packed, invisible suitcase. Mathematically, it's an array of numbers compiled by the encoder that holds the complete, deep semantic meaning of the entire input sequence. The encoder essentially packs this suitcase full of meaning, slides it across the table, and the decoder unpacks it to build the translation in a totally new language. Now, what's really wild is the sheer scale of this suitcase. When engineers set up one of these AI models, they have to decide the size of this context factor, which directly matches the number of hidden units in the encoder. A textbook diagram might show a cute little vector size of maybe 4, but real-world machine translation, it uses massive arrays. We're talking sizes like 256, 512, or even 1024, just to capture all that rich, messy complexity of human language. And here's the coolest part about this sequence-to-sequence logic. It's not just for flipping Spanish to German. This exact same architecture is out there powering a massive array of AI tasks right now. Think about it. Summarizing a huge document, generating snappy dialogue for a virtual assistant, parsing raw data, or incredibly, even writing computer code. If you're mapping one sequence of information to another, seek-to-seek is the fundamental engine running the whole shebang. All right, let's jump to Section 3, training multi-layer RNNs. This is where we really level up the system. To tackle truly complex translations, we use recurrent neural networks, or RNNs, that look at two critical things at every single time step: the current word itself and a hidden state carrying the context of what just happened. By stacking multiple layers of these networks, we build a sort of hierarchy of understanding, neatly bookended by a start and end token. The lower layers, they're kind of like your pedantic middle school grammar teacher, computing basic stuff like parts of speech or spotting a company name. But the higher layers, they grasp the deep stuff. They're looking at overall sentence structure, the true semantic meaning, and even picking up on whether the emotional vibe is positive or negative.
So how on earth does the AI learn to do all this? Well, it relies on a relentless feedback loop. We feed the system a massive parallel corpus of text. As the decoder tries to generate target sentences, it checks its word by word against the correct human-translated data. If it messes up, it calculates a loss, specifically a negative log probability. And because seek-to-seek is one single unified system, this loss calculation is absolutely crucial. It allows the system to backpropagate and simultaneously tweak all the parameters across both the encoder and the decoder at once. Next up, Section 4, Beam Search and Decoding.
So we've covered encoding and training, but let's zoom in on the exact second the AI unpacks .context suitcase and has to actually choose which words to spit out. Imagine a chess grandmaster. They don't just stare at the single most obvious next move, right? They're calculating several branching paths ahead. That is exactly what beam search decoding does. Instead of the decoder just grabbing its immediate best guess for the next word and hoping for the best, it keeps track of the K most probable partial translations at every single step. These branching paths are what we call hypotheses. So the crucial point here is the size of that K, which is known as the beam size. In the real world, K is usually set somewhere between 5 and 10. That means the AI is actively juggling 5 to 10 distinct ongoing sentence paths at the same time. It weighs these multiple paths to guarantee it ends up with the most cohesive overall translation. Because if it just blindly committed to a word that looks good in the short term, it might totally wreck the grammar by the end of the sentence. Of course, beam search has a few quirky mathematical nuances. Each of those hypothesis paths gets scored using the log probability of whatever the system has generated up to that point. But because it's multiplying fractions, longer sentences naturally end up with lower overall scores. It's just how the math works. So, to stop the AI from unfairly favoring really short, choppy translations, the system forces something called length normalization. Oh, and fun fact, while it is ridiculously effective in practice, mathematically speaking, beam search actually isn't guaranteed to find the absolute perfect optimal solution every single time. It's just a really, really good heuristic. Finally, Section 5, Scoring and Low Resources. This right here is the final boss battle of machine translation. How do we objectively grade the AI's homework, and what do we do when we want to translate languages that don't have a massive footprint on the internet? Well, first, to grade it, we use a metric called the BLEU Score. Basically, we bring in expert human translators to whip up some top-tier reference translations. Then we compute a hard mathematical similarity score by comparing the machine's attempt directly to those human benchmarks. It's a way to give engineers a concrete, undeniable number to prove the AI is genuinely getting smarter. But what happens if you just don't have a massive parallel data set for the AI to study? For those low-resource languages, engineers have to get pretty creative. They might fall back on older techniques like phrase-based machine translation or try out cutting-edge neural unsupervised machine translation. Or, my personal favorite, they use a clever data augmentation trick called back translation. Basically, they artificially bloat their training data by translating things back and forth when real human translations are scarce. Behind the curtain, pulling this off requires some serious heavy lifting in math. Now, don't get bogged down in the jargon, but just know the system leans hard on supervised learning principles. It is relentlessly trying to minimize cross-entropy loss while maximizing the log probability of whatever human reference translations it does have. It pulls off this optimization magic using something called stochastic gradient descent, all while babysitting hyperparameters, like injecting deliberate noise, just to make sure the model actually learns the underlying patterns rather than just blindly memorizing the tiny bit of data it was giving. Which leaves us with a pretty wild thought to wrap up on. We've seen how these models can literally pack the soul of a language into an array of numbers, and then decode it by exploring multiple futures at once. As these context vectors keep growing larger and those multi-layer RNNs get even better at grasping deep, subtle semantic vibes, what incredibly complex forms of human communication will these seek-to-seek models decode next? Honestly, the journey from Cold War code breaking to this elegant neural architecture just goes to show language is really just another puzzle waiting to be solved. Thanks so much for joining me on this explainer. Keep that curiosity sharp, and I'll see you next time.